All right, we should be on the air with Dr. Raymond Pete. This is Politics and Science. I'm the host, John Barkhausen, and today we're going to be talking about human health and the physiological implications of some of the chemical processes that happen in the body, namely reduction and oxidation and some of the other factors. My guest today is Dr. Raymond Pete. He has a PhD in biology and specialty in physiology. And Ray, do you want to add anything to that?
When I was studying for my degree at University of Oregon, I got interested in oxidative processes as they relate to aging. And I've been thinking about what oxidation means and all the ramifications for 40 or 50 years, and still am curious how it really works.
I see. So it's an ongoing scientific endeavor, I suppose, understanding it.
The idea of electrons moving around in matter, that's one of my longest standing interests. I think it started when I was a little kid, probably, but I'm still not satisfied that anyone knows what an electron is or how it works, but without knowing that, you really don't understand what's going on in oxidation, reduction, pH, free radicals, and so on.
Yeah. Maybe you could give us a little sense of the history of people trying to understand biochemistry. How did it all start, do you think?
The famous first demonstration that life processes are material chemistry was when a guy synthesized urea, and people had believed that that was maybe done by something special in the life process that couldn't be imitated in the real inert world, but just heating things, ammonia and carbon dioxide. I don't remember the exact chemicals, but it was demonstrated that you can make urea simply mechanically, and so people started thinking about the chemical processes that make up life, and gradually getting away from the idea that there is something unique about the life process that is distinct from chemistry.
I was just reading about that was a Swedish person, is that correct? Who figured out urea?
I think it was, yeah.
Yeah, and that was, I think, around the Revolutionary War, 1760 something. But people must have experimented with bodily fluids before then. Was there much research done?
In the 18th century, people were really figuring out a lot about how organisms work, but the official science stuff that got published and approved of by the government, that was a very slow process that was usually 100 years behind the people on the ground who were really thinking about how things work.
I mean, science, for a large part, this is my understanding, was actually a private affair done by usually wealthy people sometimes, or not always, I suppose, but...
rich cranks. So they often put their particular philosophical or religious bent into the physical ideas. And it was because of that personal quality, science was really more literary and interesting and artistic before the universities took it over. And gradually, in physics, I guess the universities took control of it away from the cranks and rich guys in the mid-19th century. And that was the physics that Einstein, for example, being the leading academic physics was being done in Germany, and Einstein, being Jewish, resented the authoritarian dogma of the professors, and so he invented something that outwitted the authoritarian physics establishment.
He sure did. Boy, and yeah, that sort of reminds me of what a general law of institutionalization that I'm making up here on the spot, but it seems like it takes the interest out of most fields once it gets franchised like that. I mean, religion, I think, used to be more of a personal experience before the church took over, and it sounds like it's the same with science.
Yeah, and I think Einstein himself succumbed somewhat to authoritarian attitudes in the case of saying what an electron is, and 30 years later, I think he regretted having set things in motion in that particular direction when he never accepted the quantum mechanics view of reality as based on randomness, and but he was largely responsible for setting that in motion with his theory of the photoelectric effect. And the idea of the electron as a discrete particle interacting with a photon as a discrete particle was the key idea in that photoelectric effect. A photon of a given energy would dislodge an electron from the solid state, giving it a certain voltage. And so you can talk about the electron energy or voltage of a given frequency of light. And that particularized or atomized the idea of both light and electrons. And that's something that allowed theory to take over and cover up and reject a lot of empirical, factual observation relating to light, color, electrons, molecules, and so on, and I think life.
Wow. So it's interesting. Once you become an icon, you have to be very careful what you say because people might take you seriously.
Yeah, I don't know how conscious he was of that, but he was very persistent in not entirely going along with the drift of the quantum physics establishment.
So that view of the electron and is atoms in general, I imagine, seeing the electron as an essential part of atomic structure. How can you explain further how that actually set us on the wrong track?
Yeah, in around the time of the First World War, Michael Polanyi had demonstrated a continuous potential description of how gases are bound or absorbed onto solid surfaces, and that was a smooth sort of process, a straight relationship between the pressure on the gas and the thickness of the absorbed layer. And when he went to Berlin to present his experimental work and theory, Einstein and others, that was already 10 years beyond the photoelectric theory and the particularization of light and electron energy or structure. And Einstein was one of the people that said in the advanced science world here in Germany, we know that that just isn't possible because matter is particulate, and you just aren't going to get forces smoothly extending away from the surface. If the surface has an electrical property and the gas has an electrical property, the first layer of gas atoms hitting that surface is going to perfectly neutralize that, so there's no potential extending through space. But Polanyi's results clearly showed that something like that was happening, a continuously thickening layer. And so Polanyi was defeated, and the people like Irving Langmuir 15 years later got the Nobel Prize for his idea that gases can only condense in a monolayer. And Polanyi knew it was wrong, but he was a physics professor, and he had to teach the Langmuir isotherm. But in his own experimental work, Polanyi went along examining how molecules and crystals, solid-state things, work. And in one area of research after another, he kept seeing continuity, things extending. For example, in the behavior of a crystal, where previously he had shown that gases on the surface of activated charcoal, for example, form multi-layers. Working with crystals, he found that the events on the surface of a crystal affected its elasticity and resistance all the way through. So physically, the surface doesn't have the meaning that it seems to in geometry. If, for example, in working a crystal back and forth, it gets weaker and weaker as it accumulates some kind of fatigue or memory. And J.C. Bose had demonstrated that sort of thing and found that the fatigue could be recovered from in a crystal. But Polanyi was interested in the fact that the weakening involves energy flowing over long distances, creating areas of exaggerated weakness. And that was the same sort of effect that he saw when the surface of a crystal was wet. The surface effect modified the resistance and elasticity properties of the depth of the crystal. So it was analogous probably to the idea of conduction bands, in which in a metal the electrons are delocalized, and you can think of particulate electrons acting this way, but Polanyi's work suggested that maybe that isn't the only or necessary way to think of electrons. And when I was in graduate school, 1969 or 70, I was reading surface physics, especially as a way to help understand oxidation biologically. And in one of the physics journals, a man named Helmut Schwartz published a description of a funny experiment in which laser light is shined horizontally through a crystal, while a beam of electrons goes through the other dimension of the crystal, through the thin layer, a layer about less than a micron, half a micron or so thick. and the electrons passing through the crystal are deflected into a certain pattern by the electronic property of the crystal atoms that they pass by. So you can see the shape of the crystal reflected in the image of where the electrons hit. But ordinarily, that's done exposing electrons passing through the crystal, exposing a piece of photographic film to the electrons and getting a chemical change producing the image. But he found taking even a fluorescent screen away, putting an aluminum oxide coated layer at the bottom that was very non-reflective. He found that the electron spots were still there, but they had the blue tint of the laser light going sideways through the crystal. And so the spots had to be the supposedly discrete particulate electrons for them to be deflected and to exactly the right spots, which are used to identify crystal structures and such. But at that spot, there shouldn't have been any light, but it was the color of the laser light modulating, in effect, the beam of electrons. And that, when I tried to talk to physics professors about it, they simply said, it can't happen. You can't modulate one electron.
Mm-hmm. And when you say modulate, you mean change color or actually?
The color of an electron is supposed to be its relationship to the atom. And what it's doing is absorbing or interacting with a particular wavelength of the light. So the atom is subtracting or maybe fluorescing a color, but it's always subtracting or adding something according to the way it is bound to the atom. So an electron flying through space it just wasn't acceptable. They preferred to say that the person was simply hallucinating or something. But it was done at Rensselaer Polytechnic Institute, and they had the best equipment of that sort in the world at the time.
Wow.
And a lot of the people immediately trying to replicate it didn't have the same degree of vacuum in their electron microscope, or didn't have the same power of laser, or the same quality of crystal making and so on. Great cleanliness and so on was part of the original experiment. So a lot of people, it's sort of like cold fusion. If it violates the theory and you don't have the same equipment exactly, it's very easy to debunk something just by doing a slightly different setup and getting different results.
Yeah, that's right. Today's genius, actually, today's crackpot is possibly tomorrow's genius in many cases.
Very recently, Helmut Schwartz, who became the head of Germany's research granting institution, the government's money dispenser for research, he said that outsiders are important everywhere, not just in science, that you don't get advanced unless you have people somewhat on the fringe.
Yeah. If anybody wants to Google minority opinions in science, there's actually a huge amount of information out there of scientists who have been sidelined for their viable research, but because it's bucking the current institutions or the money that's coming into those institutions, they're not getting any traction with any of their work. And in fact, a lot of the research is being taken away from them, research facilities. So it's a lot bigger faction of science than anybody hears about because, of course, they don't get any press either.
And I've been noticing that institutions like the Wikipedia, supposedly the internet should be an opportunity to disseminate dissenting ideas, but the culture of authoritarian science is so strong that you see it affecting the way Wikipedia works. It's sort of like a sounding board for the most authoritarian viewpoints in science.
Yeah, and that makes sense because if you have the money of an institution behind you, you have the money to pay a staff member to keep updating Wikipedia and editing anybody's other input. So it's kind of like he who has the most resources wins.
Yep.
The argument. So I was a little confused about the particulate electrons versus is it a wave theory? Is the alternative or one of the alternatives to that? What's wrong with the particles?
Well, since you can't explain many events in terms of particles, it becomes a sort of mathematical magic to try to make up theories to explain results like Polanyi's or Schwarz's. And Albert St. Georgi used conventional quantum thinking about electrons and went a long way towards explaining some of the biological phenomena that people hadn't been able to even perceive. But that doesn't mean that it necessarily validates the particulate electron just because you can explain some important phenomena. And so I think it should mean that the whole idea of what matter is, how an electron works, whether it might be that there is an electrical ether-like material which breaks up in different ways into apparently discrete electrons, but that rather than being an eternally discrete particle like a proton is supposed to be, the electron might be sort of an ad hoc diffusion, which the wave interpretation is approaching that idea that and some of the subatomic thinkers are saying that maybe this great variety of subatomic particles being seen with high energy research, maybe these are just sort of an ad hoc response of matter to a particular context or environment or stimulation.
Mm. So it might just be an aspect you're seeing depending on the medium you're using to see it with.
Yeah, exactly.
I see.
And that would say that in a different solar system or different galaxy, the atoms are not necessarily going to be the same exact, have the same functionality. And that is an implication of Halton Arp's comments on his galaxy photographs.
Okay, now that you brought that up, you better explain what that means again.
He showed that what appear to be continuously connected groups of stars, one of the parts of what seems to be a continuous stream of stars, one of the parts will have an extreme redshift difference from the other one, meaning that they should be very remote in space, but his pictures show connections like one is being shot out of the other. And he suggests that the one being shot out is newly created, and that new matter has a different way of vibrating, which shows up as a redshift. In other words, the atoms are different when they're fresh.
I see. And you said, I think last time or another time we talked, that a redshift means something's moving away from you. Is that in space?
Yeah, that's the standard mechanical physics connection, like the Doppler effect when a train passes, the frequency drops.
I see. So, but you're saying it also could have other implications.
Yeah, for example, light passing close to a star has a frequency shift. And an Israeli physicist, astronomer named Dror Sadeh was working in the U.S., and he was studying at different times the light of a star passing close to the sun, and of a beeping quasar pulsar that sends out a certain frequency passing close to the sun. And he kept seeing what seemed to be a time change or a frequency change depending on how close the beam came to the sun. And he got an atomic clock at the U.S. Bureau of Standards and mounted another one on a truck and connected them by radio so that they could be synchronized, and then drove up the coast. I think he went up towards Maine, and meanwhile recorded the relationship between these two clocks as he went, and saw that every morning at sunrise, Washington, D.C. seemed to be redshifted away from his truck. And his argument was that something about the field of the sun coming on the scene was shifting the radio waves that were connecting the two clocks. Otherwise, it would have looked like you had an expanding universe to a ridiculous extent in which Washington was moving at 1,000,000 miles an hour away from Maine.
Well, I think it may be. They seem remarkably out of touch with real life. Anyway. Well, that's fascinating, Ray. And so we're talking about the nature of the universe and ourselves, and particularly electrons, I guess, in electrical fields. So you're saying that the sun's electrical field, when it, or maybe it isn't even electrical, but the wave from the sun of radiation is possibly altering time slightly.
I think he was thinking in terms of gravitational field. But I don't know exactly what sunrise would mean.
Okay.
In terms of his thinking.
How do you spell his name, Ray, so we could go look up on the internet what he's up to?
First name D-R-O-R.
Okay.
Sadeh, S-A-D-E-H.
Okay.
Name.
Okay.
He was killed by radiation poisoning in the non-atomic bomb laboratories in Israel.
Oh, right, the non-atomic bomb laboratories making the bombs they don't have.
Yeah.
Yeah. That's terrible. So, obviously, it makes a difference how you think about electrons, and if you're trying to figure out how these molecular processes are happening. And this show was going to be about physiology, but I guess it makes a real difference if what your general theory of atomic structure is.
The idea of the particular nature of matter sort of spread or diffused into the thinking process, so that atoms, the same way Einstein couldn't tolerate multi-layer absorption in 1915, biochemists can't tolerate long-range processes in biochemistry. And one of the things in chemistry that resembles what Polanyi was seeing in crystals and his other experiments, the inductive effect is at the basis of really fundamental biological thinking about coacervates, for example. Bungenberg de Jong founded a line of thinking that eventually led to Gilbert Ling's way of seeing the cell as a special state of matter. And one of the basic and simple chemical physical principles necessary to think this way is called electronic induction in a molecule. And when you have atoms that are electron withdrawing, or they have an affinity for electrons, you put them in a molecule, and the charge or the intensity of the electron's effect shifts down the molecular chain towards that electron withdrawing atom or group. So it's like a partial electron, and that's an essential part now of organic chemistry, that you have partial charges. But when you really take that seriously and see that this effect exists everywhere in every molecule in the cell, it goes to another level, which is the coordinated or coherent effects of the electron inducing groups. So you have a collective kind of reaction in which you pass a threshold, sort of the way liquid water passes to solid water. They can be at the same temperature, but someone has to start the process, and then it can go like a cascade all at once. The atoms will fall into place and change the state. So you can have solid water at somewhat above the melting temperature, or liquid water well below the freezing temperature, if you don't have this cooperativity of molecules and atoms. And when you combine these ideas of cooperativity and induction, you get these group effects where you have a change of state, in effect, which will pass through the bulk of the material, so that you can start thinking about how it works with looking at the effects of pH on a protein.
Okay.
But that's the simplest effect of the pH, all the same all the way through a solution and a protein with its various charged groups responding to that pH, so that the internal fields are intensified or decreased according to the pH. So you can have a protein expanding or collapsing according to the pH of its surroundings. But then when you add other molecules binding or associating with that protein, and those have electron withdrawing or donating properties, then the way that protein responds to a certain pH is different.
I see.
And these electron withdrawing molecules are, in a sense, a partial oxidation. Oxidation being taking away of electrons.
Mm-hmm.
So the degree of oxidation in a molecule defines how electron withdrawing it is, and the totality of molecules with that quality in a system such as a protein or a group of proteins in a solvent, that will affect the global degree of oxidation of the system. And when it reaches a certain point, and instead of just one protein collapsing or expanding, you get the same freeze-melt transition in which one protein triggers another one, and so on.
I see.
So you get coherent, cooperative types of changes throughout the system. That's where the tending to think discretely has been so strongly affected by the particulate electron, particulate proton, particulate photon type of thinking, so that people don't like to get involved in those cooperative global effects.
I see. So I don't know if I probably got this confused, but it sounds like there's several things that affect how quickly a chemical change happens in the body or elsewhere, and that one of them is the environment. So the pH surrounding the substance where the change might happen is key, and then the other part is the materials that are attached to that substance. So if you're talking protein, and then the protein might have other molecules attached to it that actually enhance or deter the change happening.
And that's one of the complexities of the living state, is that if you kill it, it doesn't work the same. So you have to think of it always in a certain environment.
Mm.
And that you have to really think of it as a flow from the environment in and out, and the rate of flow and intensity of flow and so on.
Mm-hmm.
The way people think about antioxidants even tends to turn into a static description rather than a flowing process.
Mm-hmm.
The cell is always, when it's alive, maintaining a delicate balance between oxidation and reduction. And so antioxidants are a dynamic process in which they're also oxidants. If you push towards a dominance of reduction, then you kill the cell in a different way.
Ray, can you back up a little bit and just explain the origin of the word oxidant and what it means?
In the 18th century, when they were thinking of phlogiston, that you had to dephlogisticate something.
What does that mean?
It was something that left a burning substance, and it meant the exhaustion when phlogiston had filled up the space. You couldn't burn anything more in it, and it made it very hard to understand chemical reactions. But then Priestley and I guess Lavoisier was another one. Two or three people around the same time were seeing that there was something being consumed from the air in the process of burning rather than added to it. And when they started studying what was being consumed in the air, they saw that it generally made an acid form. And so I think it was Priestley who named it the substance that makes burning possible in the air. He called the acid former, or the oxygen, oxy being the root for acid or sour.
Mm-hmm.
And so many acids were formed by oxygen. It got its name as the source of acid.
Huh.
And it isn't an absolute. There are acids without oxygen, and that leads into the whole issue of pH. But thinking of oxygen in relation to its ability to form acids, that's a very important to integrate with your thinking of what a cell is doing. And people tend to have begun thinking of carbon dioxide as simply a waste product. But if you think of the electronic balance between oxidation and reduction, holding the proteins and other things of the cell in a certain very specific state or conformation, changing the pH is crucial, and this partial oxidation that you get at a lower pH, which governs the arrangement of the protein and other substances. Carbon dioxide turns out to be a universal balancing factor or adjuster of the acidic properties of the protein. So the acid formed by oxygen, in this case carbon dioxide, it's in itself it's an acid as defined by Gilbert Lewis, and it doesn't have the protons, so you needn't talk about the pH really, because it's a non-protic acid, just two oxygens and a carbon. But this arrangement, an oxygen doubly bonded to a carbon, creates that electron withdrawing property, the intrinsic partial oxidizing property of that molecule, which when it attaches to a protein, it increases the acidity of the protein, making it slightly, partially more oxidized, more acidic. And that changes its affinity for other things according to how negatively charged its groups are. And this is the kind of thinking that led up to the Gilbert-Ling orientation, accounting for cells and their metabolism without the hypothetical membrane and its pumps. The pH and the acid property of the protein system maintained by the carbon dioxide produced by oxidation. This is the central thing in explaining why cells can discriminate between sodium and potassium and calcium and magnesium and all of the discriminations that cells make. You don't need a little magic pump moving things in and out that would consume more energy than the cell has. The energy of the cell is really being produced to form carbon dioxide, and the carbon dioxide is changing and maintaining the properties, preventing excess electron accumulation. And since it's a continuing streaming process, you have oxygen streaming in and carbon dioxide streaming out. And the carbon dioxide reacting as an acid with water shifts the property of the water atom, so the water joins with the carbon dioxide, forming carbonic acid, which ionizes. You now have a negative charge on the carbon dioxide streaming out of the cell. It takes positive charges out with it. Otherwise, the cell would quickly become highly electrically charged. So the movement of oxygen in, carbon dioxide out, is taking out the sodium and calcium as a streaming continuous maintenance process.
Wow. So this is most people have heard of the membrane theory of cells, that they're basically bags holding this cytoplasm in. And this is, in case you didn't get this is an alternative theory that it's actually being regulated by the products of the mitochondria. Is that right, Ray? So the mitochondria is producing the CO2 when it makes the energy we all use, the ATP. And so the CO2 starts off as an electron acceptor, but then it becomes negatively charged, and that bonds with the positive metal ions, the magnesium and calcium.
It doesn't necessarily bond with them, but in leaving, they tend to get dragged out too.
I see. And why is the CO2 leaving?
Just because it's being constantly formed inside, and it just diffuses out down the gradient.
So that's like an osmotic pressure? No.
Yeah. Well, a diffusion pressure. It's going down the gradient. Like if you put alcohol against water, they'll tend to mix. The alcohol will move into the water, and the water into the alcohol until they're more or less even. And when you have a high concentration of CO2 in the cell, at a certain point it starts being more at ease outside of the cell.
I see. So it's a diffusion process.
Yeah, and that accounts for taking it out into the extracellular space in the blood. And when it gets into the blood, it having taken the sodium and some other things with it, it circulates to the lungs and changes back to carbon dioxide, which is again going down its gradient from a high concentration in your blood to a lower concentration in the fresh air you breathe. So the carbon dioxide is leaving the blood, and it leaves behind the molecules or ions that it took out of the cells. So the absence of the acidic carbon dioxide in the blood leaves the blood now with a higher pH because of the movement of sodium and such out of the cell.
Hmm. I see.
The normal situation is for a healthy cell to be just faintly under neutrality, and for the blood to be definitely over neutrality, like inside the cell 6.9 pH and in the blood 7.4 roughly.
Okay. 7.4. I see. So that's a little bit higher than the cell is low.
Yeah.
Yeah, go on.
A lot of people have seen disease as caused by a low pH or too much acidity, and in the case of stress and cancer, a tumor will become very acidic. So that traditional idea has a basis that an infection or a tumor, the inflammation produces high concentration of lactic acid and a very low pH in that area, which does have disruptive toxic effects on that area. And so the body is able generally to correct that and reduce the inflammation and stop the production of lactic acid. But when lactic acid is formed, the conversion from pyruvic acid to lactic acid is drawing an extra proton out of the NADH catalyst that causes the conversion, and in taking away this extra proton as it leaves, it in its formation, it raises the pH inside the cell. So even though a tumor or an infection is locally, you see excess acid, high lactic acid, inside the cell that's doing that, it's the reverse process. You get an increase in the pH inside the cell. And so the cell which is stuck, if it gets stuck in producing lactic acid because it can't produce CO2, then that means it also tends to get stuck at a higher pH, and this higher pH changes the whole system, and that's where you tend to get a self-replicating tumor, because the normal acidic conditions maintained by the CO2 are lost.
I see. Okay, that's good to know. And maybe you could explain for us. I don't think you have to go through the entire cycle, but you're talking about cellular respiration, and I don't think people generally know that pyruvic. When you're talking about that, you're talking about the products or the process of making the energy that we all use. And could you just give us a little Cliff Note version of that?
Yeah, looking at us in our environment, we're really sort of sandwiched between the sugar energy we get from plants and the carbon dioxide that we make as the final product of the energy from the sugar. And a series of changes in the sugar molecule, each oxidation of that molecule adds a little chemical energy to the cell that the cell can use to make proteins. As it degrades the sugar, it builds up amino acids and proteins and fats. And when you're unable to oxidize the sugar all the way down to carbon dioxide and produce lactic acid instead halfway, you're losing the greatest part of the energy stored in the glucose molecule. And that lack of energy has its repercussions. But when there's really a lack of oxygen, to continue the oxidation, that NADH, which allowed pyruvic acid to take this shortcut off into the semi-toxic lactic acid, that has to be renewed before you can even make another lactic acid. So without oxygen, you need some kind of oxidant to even continue producing that kind of low energy from sugar to pyruvic and lactic acid. And to do that, cells can produce fat and get rid of their electrons by building them into fat. So building fat, in a way, is an alternative, very bad one, to using up oxygen and making CO2. So interestingly, cancers which get stuck in the exclusive use of converting glucose or amino acids to lactic acid as their energy supply, they also get stuck making fat. Fat becomes their oxygen, in effect. And then when they still have mitochondrial function, the cell burns fat as its energy source. So it's really a deranged and crazy kind of metabolism to produce an irritant, lactic acid. And to do that, it has to make fat, which is then used as fuel with its own consequences.
And is that's called glycolysis?
Yeah, it's aerobic glycolysis when you make lactic acid in the presence of oxygen. And ordinary anaerobic glycolysis is what happens when you exercise too hard. You can build up lactic acid in getting out of breath. The blood lactate increases if you exercise faster than you're breathing, and that's normal. You can a little later consume and oxidize the lactic acid, and that's okay. But when you start producing lactic acid even in the presence of oxygen, as in the case of cancer, or extreme trauma or shock, same thing happens. Something turns the trigger so that even though oxygen is present in shock, you will waste your sugar and make lactic acid.
I see. So oxygen is there, but it's not. You're unable to use it.
Yeah, and the nervous system is, in the case of shock at least, the nervous system is involved in making that aerobic glycolysis. And so there are quite a few people who have suggested that the nervous system is involved in the cancer transition, doing the same thing that shock and trauma can do acutely.
Wow. I have to take a short break here and say that you're listening to WMRW LP Warren, and we're streaming live at WMRW.org or 95.1 FM, and you're listening to Politics and Science. I'm John Barkhausen, the host, and my guest today is Dr. Raymond Peat. He's a has a PhD in biology and a specialty in physiology. And we're talking around the subject of oxidation and health, and what role oxidation plays in maintaining that health. There's more I want to ask you about the not being able to use the oxygen that's present in anaerobic. It's anaerobic glycolysis, even though there's oxygen there.
Then it's called aerobic.
Oh, and then it's called aerobic glycolysis. I see. And how does the mitochondria make do with burning of fat? How is that even possible?
It's
and what are the problems with that?
It produces less carbon dioxide, for example.
Mm-hmm.
I think that's the main problem. If you develop fat stores, you get particles of fat accumulating in the cytoplasm and maybe in the nucleus that probably have a disruptive effect when you're heavily shifted over to a fat economy.
I see.
If the tumor makes saturated fat as its first product in converting sugar to saturated fat.
Mm-hmm.
But when it's shifting in the presence of stress, when it shifts to burning fat, usually that will go through your fat stores, burning up your subcutaneous fat quickly. So when a person is very sick with cancer, for example, they get a gaunt, emaciated look as their superficial fat stores are used up, and at the same time they convert amino acids to energy, converting some of it to sugar and some to fat, and so it starts a wasting process. But our stores, the older a person gets, generally the higher the amount of polyunsaturated fat in their stores. And when you're oxidizing polyunsaturated fats, that produces more oxidative damage to the mitochondria. And so it tends to lower the oxidative part of metabolism and slow things down in general.
I see. And then people end up feeling a lot less energy levels and generally get run down overall.
That happens in midlife to lots of people. That it resembles the cancer metabolism, but it just shows up as fatigue, low energy use in general. Some people, where textbooks used to say that you would always lose weight if you ate less than 1,700 calories per day. Lots of people can maintain their weight on 700 calories a day. And that requires turning off of the thyroid function to a great extent. And so you're being wasteful, even though you're not using very much energy at all. What you are using tends to be poorly used and destructive. So you tend to reduce your connective tissue and muscle and digestive system and so on, rather than just living on what you're eating or stored fat.
Mm-hmm. Wow, so basically hibernating.
You got fuzzy. I couldn't tell.
Maybe are we breaking up again? Can you hear me now, Ray?
It's very gurgly.
Okay, I'm going to call you back. And we'll resume.
Okay.
Okay, bye. Hello, you're on the air. Can you hear me?
Yeah, you're still a little
Still gargling.
or
Huh.
not as bad as it was.
Okay, you're coming through fine. So
Okay.
if you can put up with it, we're good to go.
Okay.
So are fats always the part of the process of respiration, oxidizing fats, or is that only when you're ill?
Um. Yeah, it's only under stress generally, and starvation
Mm-hmm.
or diabetes or a high level of stress.
I see. A lot of people are on those ketosis diets where they don't eat any carbohydrates. And does that cause you to burn fats?
And protein.
And protein, right.
Your brain and some other tissues, the intestine and red blood cells and various uh, little areas, but especially the brain, have an absolute requirement for some sugar, some glucose, and they'll get it by breaking down amino acids, and they get that from eating your tissues if you aren't eating enough amino acids. But if you are eating amino acids as your energy source, fats and amino acids, you turn on the machinery for turning amino acids into glucose and fat, and running that machinery involves turning on stress hormones. A whole range of hormones adjust to it, and I think those have chronic harmful effects.
I see. So I know when people do it, they're usually in a very controlled setting. They go in for regular checkups, and I don't actually know, but I think they take blood and urine samples, and they're trying to make sure you're not actually endangering yourself.
Most of the proteins that are being eaten under those systems, most of them are too high in phosphate, and usually too high in methionine, cysteine, and tryptophan. And cysteine is an excitotoxic amino acid, and methionine is involved in stress and aging when in proportion to its excess, so that one of the most effective life-extending diets is simply to reduce the amount of methionine in the diet drastically. So the sulfur amino acids and tryptophan are stress and aging promoters, especially excitotoxic damage to the nerves. And the high phosphate for most of the popular proteins, the high phosphate has a lot of excitatory harmful effects. The clatho gene and protein that is deficient in animals that have a very quick aging process, that's largely a phosphate handling protein, and the rapid aging produced by lacking that protein and gene involves accumulating excess phosphate.
And phosphate you get from eating meat primarily, or?
Meat is one of the highest ratios of phosphate to the other minerals, but several of the very high quality proteins, even mushrooms, have a pretty high ratio of phosphate to calcium. Milk and cheese are about half and half, which is probably safe, but fruits and leaves, leafy green vegetables, have a very safe, very low phosphate content relative to calcium and magnesium and potassium.
I see. So fruits and vegetables are the best, but you're not getting much protein in that case, so you need some milk and cheese too?
Yeah, and probably a fairly low protein diet is very good for the health, but in the sense of living a long time, but for maintaining tissue renewal, you can't go below a certain amount of tryptophan, cysteine, and methionine. Those are rapid turnover proteins.
Okay. I think, Ray, I'm going to turn to some of the questions I received from people in preparation for this show, because I know if I wait, we're going to be short on time, and I want to make sure you have time to answer them. Last week we talked about, or you mentioned, Luca Turin and his research on, I think it was odors and the electrical nature of odors. He had, maybe you could, when you get to answering this, you could go over that a little bit. But somebody wanted to know what your feelings are about multiple chemical sensitivity, and that's pretty common these days. A lot of people can be made very ill by a perfume or the smell of bounce. And what do you think is going on, and does that relate to Luca Turin's work?
Yeah, I think it does, and he was talking specifically about smell and psychoactive, like antidepressant chemicals, and there's, when you look at the what's in common between smelling and having the antidepressant effect of some chemicals, what's in common is the resonance state, or the tuning of the molecule to the oxidation state, which is in this context of partially oxidized proteins in a coherent cooperative system. The whole system has to be tuned to a certain level of reduction and oxidation, and the addition of a chemical, whether it's an antidepressant or a perfume molecule, passes along the conductive pathways of the nervous system, and the cells all through the body are involved in delicate nerve balances. The vegetative or autonomic nervous system regulates the state of inflammation of the tissues, for example. There are lots of cells closely associated with fibers of the nervous system, cells called mast cells, for example, that can regulate inflammation all through the body, in the brain as well as all the other tissues, and these are connected and balanced with the nervous system. So a slight shift in your autonomic nervous system can globally change the degree of inflammation all through your body, increasing the amount of histamine and serotonin and the various products of the mast cells. This is when a person is under stress chronically, these inflammatory things tend to rise, and when you increase your intensity of mitochondrial respiration and your level of carbon dioxide, that stabilizes the system, backs away from that excess inflammatory reductive impulse. But when you're right on the edge, just balanced, not intense enough oxidation going on, then perfume molecule or a psychoactive chemical or a food molecule can send impulses through your system, shifting you away from the oxidative excitatory processes towards the side of your nervous system that becomes dominant in shock. So I think the chronic fatigue and chemical sensitivity, inflammatory states are in effect a variation on the physiology of shock.
That's really fascinating. I mean, it's amazing that somebody can actually wear a product because they like the smell, but that same product, the smell of which can make somebody else deadly ill.
Yeah, I think it depends on the way your nervous and chemical system is tuned up.
I mean, everything, oxidation and reduction is involved in all of our processes that are chemical.
Yeah, the lactic acid is a reductant as well as a product of being reduced, and turning it into lactic acid from pyruvic acid involves an electronic addition or reduction. But it then, when it goes to a balanced or healthy cell, it shifts the balance towards reduction. And if you have oxygen in that cell, it's okay. The electrons will be consumed. But lactic acid itself has this potential for shifting the balance. For example, in the mast cells that are signals for more inflammation, too much lactic acid will activate their releases. So systemically, letting too much lactic acid circulate is adding to the inflammatory state.
And I know you've told me before, people might be interested in this, that you're not very fond of yogurt because of the lactic acid, so you can actually absorb lactic acid from your food directly. I mean,
yeah, there are some kinds of yogurt that have very little lactic acid. You can thicken the milk enzymically rather than with a lot of acid. And those very mild yogurts aren't especially harmful, but if they're very sour with lactic acid, and if your liver is on edge, not enough thyroid function, then that slight shift towards the reduction side can have systemic effects and can bring on allergic reactions, migraine headaches, and such.
And so, just talking specifically about yogurt, if you we have a local yogurt maker around here, and I find if you buy it immediately, as soon as it comes out, there's hardly no apparent lactic acid in it. But the longer it sits, the more the acid separates from the actual milk product. So I'm wondering, is that acid forming as it goes, or is it always in there and you just shouldn't eat it, period?
No, the bacteria are making it.
Okay. So a young yogurt would be fine.
Yeah, I think so.
Okay. Yeah, because you can also strain your yogurt, which is the same as buying Greek yogurt, and that gets rid of it and basically makes a thicker or cheesier product.
Yeah, that's the idea of cottage cheese. They drain away most of the fluid, the whey, and that takes away almost all of the lactic acid from most cheeses.
Okay, well that's good to know that fresh yogurt is okay. I guess got a question coming in on the same subject we were talking about a second ago. This is from Duncan. I bought a perfume base from a chemical company some years ago, and it was so toxic that UPS was afraid to deliver it. I had to go pick it up myself. On the MSDS toxicity scale, which goes from 0 to 4. This was a 6. Yep, 2 points over the max for chemical toxicity. Perfumes are very poisonous, he concludes. What's the MSDS? Is that the manufacturer's
safety data sheet, I think.
Thank you, yes. All right. And he also asked, do you contribute to Wikipedia?
No.
Okay. And, go ahead.
Someone has asked me to comment on the association induction hypothesis article, a very good long article describing Gilbert Ling's theory. A lot of people are jumping on it, saying that it should be eliminated from Wikipedia because it's wrong.
Wow. Well, that's surprising. I wonder if Gerald Pollack, who also basically derived a lot of his work from Gilbert Ling and says so, I wonder if he might be there defending him.
Yeah, I don't know how you get involved. When I find out, I think I'll say, keep it, please.
Yeah, okay. That would be good. Let's see, and I have some more questions here. I'm going to find them so we get to them before the show is over. This is from Paul. He says, I am a 34-year-old male, and since about 8 months, type 1 diabetic. I believe I got diabetes after x-rays from my dentist. I'm curious if you think that's possible. I take daily insulin and follow a pro-metabolic diet. I supplement aspirin, vitamin A, vitamin E, vitamin K, B1, B3, glycine, pregnenolone, magnesium glycinate. I am still in a so-called honeymoon phase, and I would very much like to prolong this phase or even get off all insulin. Do you have any tips or supplements I might add to my regimen? And he says, thank you from the bottom of his heart.
Before I was born, my father had extreme diabetes, went down to something like 90 pounds or less, couldn't assimilate any kind of food, even pure protein, raised his urine glucose tremendously. And looking at old naturopathic remedies, he started eating as his only food brewer's yeast. He ate, I guess, 2 cups a day at first, and immediately stopped producing so much glucose in his urine, and in a few months was completely well. Every maybe 5 years or so after that, he would eat some extra brewer's yeast, but never had any symptom of diabetes after that. And I think part of that effect is the hormones in the yeast, which stimulate regeneration, and high potassium content, which has an insulin-like action, and the high B vitamins. But having enough glucose so that you don't draw any polyunsaturated fats out of storage, those are very toxic to the insulin-producing cells in the pancreas. And they are normally, they're constantly turning over. The beta cells are being renewed constantly, and in a diabetic, they're being renewed, but they die quickly. And sugar is a factor that will prolong their lifespan. It doesn't need anything to stimulate renewal, just to prevent them being killed primarily by the polyunsaturated fats. And the nitric oxide is soon after it was discovered that the body produces its own nitric oxide. In the early 90s, many articles came out demonstrating that nitric oxide is specifically what kills the beta cells. And so you definitely don't want to do anything that would increase your nitric oxide production.
What kind of activity does that?
Supplementing arginine or foods high in arginine wouldn't probably be desirable.
Okay.
And I think the effects of aspirin and the B vitamins and the vitamin E, pregnenolone and progesterone, and DHEA around 1985, I think it was, someone gave rabbits diabetes with a chemical toxin and then gave them a supplement of DHEA. And that was the only difference. The ones that got the DHEA regenerated healthy insulin-producing pancreases.
And that has to be taken in small amounts, or you convert it to estrogen, is that right?
10 to 15 milligrams is probably a safe amount.
All right, and one of the things that I think everybody will be surprised by is that you're actually advocating taking sugar or glucose. Which is
a couple of my articles on my website give some of the history of that. In the late 19th century, a couple of doctors described cases that they cured from really advanced terminal diabetes, people losing weight at a terrific rate. They added something like 12 ounces per day of sugar to an otherwise good diet, regular high protein and vegetables and milk and so on. But just by adding 12 ounces of sugar to that diet, in just a few weeks, people came back from near death.
And I guess their logic was, since they were urinating out so much of their bodily sugar, they figured maybe they were short on sugar.
Yeah, exactly. Their reasoning at first was they're dying so fast that they're putting out the equivalent of a pound of tissue converted to sugar every day. And just to slow down their starvation process, they said, and they crave sugar, why not let them eat what they crave and maybe slow down their death, but instead they stopped wasting away and came back.
And I want to go back a little bit to, because I think I did, the person who asked the multiple chemical sensitivity question a little short shrift, and that I never asked you, what can somebody do if they're suffering from multiple chemical sensitivity?
Supplementing thyroid is the usual thing, but sometimes they're very low in cholesterol, and since thyroid works partly through converting cholesterol to hormones like progesterone, DHEA, and pregnenolone, if your cholesterol is too low, thyroid alone doesn't necessarily do it. So supplementing one or more of those will very quickly often relieve the exaggerated sensitivity.
Okay. And it sounds like you said that the rabbits were given diabetes just by being poisoned with a toxin, and it sounds like that's happened. A lot of our diseases are actually environmentally caused. It's, I know they say a lot of people have predispositions to cancer and diabetes and stuff like that, but I personally suspect a lot of it is just environmentally from the pollution that's inevitable in our industrial society.
Yeah, when I was starting on my dissertation project, I wondered what the factors were that slowed down oxidative processes in aging. And as I looked around the possibilities, I saw that the same type of deterioration, the same biochemical patterns of interference with mitochondrial respiration were produced by a great variety of stresses, radiation, ionizing radiation, or even ultraviolet to excess, had an effect similar to all of the estrogens and the aromatic hydrocarbon carcinogens and hydrocarbons that produce excitation and inflammation, and polyunsaturated fatty acids produce the same pattern of deterioration, and the vitamin E supplement was found to stop the characteristic damage they were seeing in lab rats and industrial animals from feeding them too much unsaturated fat. And my thesis advisor found that the effects of too much estrogen were corrected by a very large vitamin E supplement. And others were finding that vitamin E protects even against radiation and sunburn. So some of the processes, like the breakdown of polyunsaturated fats, are increasing our susceptibility to damage from all of those stressors: radiation, estrogen, toxic heavy metals, and so on.
Mm-hmm. And Ray is referring to the liquid oils that are everywhere in our food supply. The canola oil. I think you think olive oil's not too bad and butter's good, but all of the vegetable oils, except for coconut, are not a good idea.
Yeah, olive oil has only 8 or 10% of the unstable polyunsaturated. Butter and coconut oil have 2 or maybe 3% of the unstable ones. I've recently finally shifted in accordance with something that I read about 40 years ago on the absence of cancer in animals that were fed different types of oil. Mm-hmm. Coconut oil was safer than olive oil, which was safer than safflower oil and the polyunsaturated, but the safest of them all was hydrogenated coconut oil. Huh. And recently I found a place to get some just to try it out, and it has a very nice clean taste and texture, and it's free of trans fatty acids as well as polyunsaturated fats. Okay. Trouble is the supplier doesn't supply at retail, only car lot loads.
So did you get a semi? Is it parked out back behind your house?
It was a very involved process to get a few gallons of it.
Wow. Sometimes you can say you're thinking of buying a semi, but you just want a sample.
Yeah.
Yeah. Well, that's interesting. Did some of the animals get to eat butter?
Oh yeah. Butter and coconut oil were the safest natural oils.
Okay. And so let's talk about, this is another thing that confuses me about oxidation reduction, is sometimes they refer to it as hydrogenation or dehydrogenation, but they're still talking about oxidation and reduction, aren't they?
Yeah, it's just the movement of electrons that they're talking about. When we turn saturated fat into unsaturated fat in our own bodies, we dehydrogenate it. And when a cow turns unsaturated fat from their food into saturated fat for the butter, it's bacteria in their intestine and rumen which is saturating it or hydrogenating it. So dehydrogenation is something that we do in our own body.
I see. And maybe you could describe for us what is actually happening to the molecule. Is it you're actually removing the hydrogen, and then that's what oxidizes it?
They're actually referring to the electron. The movement of electrons out of the bonds is what makes the difference, and the usual thing that you move is a hydrogen atom or two hydrogen atoms.
Mm-hmm.
And when you take those away, like if it's on the two adjoining carbon atoms in a fat molecule, there was a bond of two electrons between the carbons. You take away a hydrogen from each one, and it takes the proton and one electron leave in each case, and they combine two hydrogen atoms, turn into hydrogen gas or go to some other molecule, and the left behind electrons join with each other, so you get a double bond, 4 electrons joining those carbon atoms. And the absence of the space-filling hydrogen seems to leave that range of electrons between carbons open and more reactive. So when you get a lot of hydrogens removed, that makes access of oxygen atoms to the fat molecule easier.
I see. So that's why Crisco is actually a liquid oil, but it's had the hydrogen added to it, and that makes it more stable.
Yeah, and if they would complete the process the way they do in changing coconut oil from 2 or 3% PUFA to 0% PUFA, you wouldn't get the trans fats in it, and so you would have totally saturated and mostly stearic acid in Crisco, and that would be safe. One group of researchers found that aged, defective mitochondria that were not respiring properly, when they gave them fully saturated, hydrogenated, I think it was peanut oil, it restored mitochondrial function.
Wow. So it's a way of purifying it.
Yeah, and it eliminates the unstable quality that makes things susceptible to oxidation. Physiologically, there's something called the saturation index. You can look at a person's red blood cells and find the ratio of stearic acid fully saturated to linoleic acid or linolenic, different degrees of unsaturation, and the longer, even more unsaturated. And people with cancer have a low saturation index. It's a very stabilizing thing to, like a newborn baby is highly saturated in its fats. In recent years, a lot of nutrition-oriented doctors are saying you must give babies fish oil and other highly polyunsaturated things, because most babies are born deficient in the essential fatty acids, but that's the normal state of a newborn animal.
That's strange, because it just shows how disconnected the medical authorities are with nature. I mean, if you'd ever look for anything for an idea of what perfection is, I think you'd look at a newborn creature.
The rate of oxidation is highest. Uh, uh, I'm not sure how much how you would compare the prenatal oxidative state, but right at the newborn, the consumption of oxygen and sugar per gram of tissue is higher than it will ever be later. And it decreases, especially at puberty with the rise of the sex hormones. The oxidation rate decreases more sharply, and mortality rate increases as the oxidation rate decreases.
Right. So that makes perfect sense. Now, I better get back to my questions here from interested people. Martin asks about salt, and these are 3 questions about salt, and I'll just run through them as quickly as I can. Can salt ingestion trigger migraines in some predisposed people? Example, Max Gearson. And what would be the what would be the physiological explanation? Shall I read them all, or do you want to take them one at a time?
Are they related to the salt?
Yeah, they're all about salt restriction.
The others.
Okay, here's number 2.
Context.
Here's number 2. Do you believe salt restriction was useful in the University of Munich's 1928 tuberculosis trial with Max Gearson's diet under the supervision of Ferdinand Sauerbruch? If yes, was the beneficial effect due to a release of excess intracellular water? And 3, if salt restriction is useful in evacuating excess intracellular water present in degenerative diseases, is it useful to keep restricting it once this excess intracellular water has been evacuated? Should cancer patients keep avoiding salt after a few months of a saltless diet?
I read Gerson's book, and he was very, very good, thorough. He saw the effects of the diet first on migraines, and then tuberculosis, and then cancer. And he tried to understand it, and he seems to have read just about everything in the first half of the century on the subject. And the salts are extremely important. The other contemporary of his, cancer researcher, had a very interesting parallel set of facts regarding salt. William Frederick Koch, who was a chemistry professor at Michigan early in the century, was studying the removal of the parathyroid glands, and a calcium supplement was the typical remedy for the cramping reaction to the removal of the parathyroid, and the doctrine was developed that the parathyroid regulates calcium, and so you need to replace calcium when the gland is removed. But Koch did the surgery on animals and found that if he gave them extra potassium or sodium or magnesium, it had the same curative effects. And the essential fact was that one of these can make up for a deficiency of the other. And the Gerson diet was extremely high in the other minerals, especially potassium. And the diet always had the amount of sodium that you would have in juice, leaves, and fruits and vegetables and so on. So it was always a physiological amount of sodium, but often a very excessive, large amount of potassium and magnesium. And I think these were the essence of Gerson's success rather than just the reducing sodium, because when you look at particular experiments, sodium can stimulate the respiration of a cell and cause it to unswell, give up excess water. If you lower the other minerals and give it too much sodium, you can force it to swell and take up water. But its normal physiological function is to act as a stimulant. Calcium tends to do the same, but the cell normally is excluding sodium, and it perceives sodium as an irritant or stimulant and revs up its oxidative metabolism when it has a little extra sodium, and the increased oxidative metabolism produces carbon dioxide and restores the balance. So when they're in balance, the right amount of sodium is increasing energy production and decreasing cell water content. And the much of this stuff hadn't been specifically examined during Gerson's lifetime, but he was definitely onto something and was curing migraine and cancer. But he very typically would give his patients a couple of grains of Armour thyroid and very often coffee enemas, and they were always having a very high ratio of carbohydrate to protein, so they were low on the methionine and tryptophan and the potentially toxic amino acids. And generally, lots of things in his program were very well founded, but there just wasn't enough information at that time about how the balance of the alkaline minerals works.
Yeah, and it sounds like there's so many variables going on there that it would be hard to pin down any one cause or.
The aldosterone. One of my first physiological experiments was on myself. When I worked in the woods, our cook was cracked on the idea that hard physical labor meant you sweated a lot and needed to replenish your salt. And so he would put, I think it was about a tablespoon of salt in everyone's porridge in the morning.
Mm.
If you didn't eat your porridge, you didn't get your ham and eggs and steak and other things. So everyone was doing it. And I within a few days of doing that, I found that the sweat that dripped down my forehead was leaving salt crystal trails on my glasses. And my eyebrows looked like they were coated with snow from the salt crystals. And I thought of the trick of saying that I had been put on a low-salt diet, so I got normal porridge from then on. And immediately I could sweat distilled water.
Uh-huh.
And on the high-salt diet, I had to take salt pills about 11 o'clock in the morning. Otherwise, I started getting faint. Needed to replenish the salt. It was pouring out so fast. But after the low-salt diet, I never needed afternoon salt pills again.
You mean the overdose of salt sort of stopped your body from being able to regulate it properly?
Yeah, and the when you're cutting back on the sodium, one of the first reactions is that your aldosterone is increased. and aldosterone lets you retain the sodium, but it does it at the expense of losing some potassium and magnesium.
Huh.
So if your diet is high in calcium and magnesium and potassium, then there isn't any problem with the low sodium intake. But chronically, that high aldosterone has a pro-inflammatory effect, and so chronically getting more of all of the alkaline minerals than you really need is a safety precaution that will suppress your aldosterone and protect your heart from inflammation and fibrosis and hypertension and so on. So in the long run, sodium has this protection against cell swelling, inflammation, fibrosis, inflammation.
And if taken in reasonable amounts, it tastes good too. And what about, can salt ingestion trigger migraines in some predisposed people?
Yeah, when you're already on a low salt diet and take salt, one of the common physiology experiments is to have people drink a quart of plain water or a quart of plain water with a heaping teaspoon of salt added to it. And at the end of the physiology lab, everyone who got the unsalted quart of water would have formed about a quart of urine, and the ones that got the salt didn't have any extra forming. And it took usually a couple days for that excess water to come out. So when you take a sudden dose of salt, it makes you swell up and retain water until your aldosterone has adjusted downward.
I see. So it just takes a while to adjust to it.
Yeah, and you'll notice anything that is susceptible will swell up. Your fingers and toes and lips and eyelids and such might swell up in the first day after you've eaten a lot of salt. But people who, for example, on a long airplane trip would always get swollen feet, if they adjusted 2 or 3 days in advance by eating extra salt and some baking soda, they didn't get the swollen feet from sitting still anymore.
Huh. I see. So, so you're retaining the you're retaining the liquid then, in a different place, or are you not?
No, you're suppressing the aldosterone, so it gets the water out of you.
Oh.
And one of the ways sodium works is the albumin molecule is full of negative charges, and it holds the sodium in association. So you get a cloud of positive, negative charges, which holds onto water. It keeps the water osmotically held in your bloodstream. If you're low in either albumin or sodium, your blood itself loses the osmotic quality, and so the water stays in your cells and extravascular spaces. But when the combination of albumin and sodium is present in the blood, water flows out of the tissues into the blood, and the blood passing through the kidneys then can get rid of the water that otherwise would sit around in your tissues. And that same situation impairs circulation because your blood volume is low and the fluid volume outside the blood vessels is too high.
Oh, I see. Right.
And the antidiuretic hormone is another side of this that is a lot more complicated and responds to stress, estrogen, and a lot of other things where the aldosterone is pretty closely related to the mineral balance.
And what is the anti-diuretic hormone? Is that, what are you calling, what is that?
It's a pituitary hormone that causes water retention with sodium loss. And a low thyroid person, old people, people after accidents, anyone in serious stress, they call it inappropriate secretion of antidiuretic hormone syndrome. And that's very common where edema is the what is really harmful. The brain swells up, for example, because the body has too much water and not enough salt. And the remedy for that is just adding sodium, but that's not fundamental. And if you do it too fast, you disturb the balance in the different compartments. But the basic reason for it is that you aren't producing the carbon dioxide from a thyroid deficiency, and the absence of the high production of carbon dioxide means that you aren't able to retain the sodium in your kidneys as the water passes through. And so the low thyroid person loses sodium because the reverse of the process that happens in other cells. In the kidneys, carbon dioxide allows the cells to catch and retain sodium.
Well, that's fascinating. And can't say I get it all, but I understand it a little bit. That's very interesting, Ray. Thanks for explaining all that. And I had more questions, but I didn't have any more from other people. I think I got to them all. And anything you want to say to sum up about staying healthy and keeping your oxidation working well? We have about 2 minutes.
Just keeping stress down and fun up, judging food by largely by how it tastes rather than by what the experts say.
Okay, well, that's easy advice to follow. So on that note, Ray, I really want to thank you for coming on these last 2 shows, and I'll tell people how to get in touch with your website if they want to read more, and I'll say goodbye.
Okay.
All right.
Thank you.
Thank you so much. Thank you so much, Ray.
Mm-hmm.
Yeah, bye-bye.
Bye.